So I am actually running a short course on expert tomography of planetary samples, and Dr. Denevi is here for that course, as is about 12 people in this room. So sorry for crowding your seminar. They're all very interested in hearing this. Dr. Denevi is the PI of the geology team for Artemis III. She got her PhD at the University of Hawaii. Then she was a postdoc at ASU for a while, and now she's at Johns Hopkins. She was participating scientist on Dawn. She worked on Messenger. She worked on LRAC. And today she is going to, she has an asteroid named after her. She's got a lot of awards. She's really great. And today she's going to talk to us about the Artemis III geology.
Yes. All right, thank you, Romy. Is there like a, can I just steal this for a minute?
Sure, yeah.
No, I have to click on the slide or something, it's not doing anything. All right. Okay. Do you wanna? Okay. Well, yeah, thank you so much for being here. Sorry, it sounds like there's a little room and snack food, so we've had a crowd and wonder that that.
Like you can come back when it's on. Yeah, that works.
Okay.
Or above your head is the back. Yes.
There. No, that's good. Okay. But yes, feel free to interrupt and ask questions. This is a great, small room where we can all chat.
Sorry about that.
It's perfect. Well, except for the people standing, sorry. So I'm working on the Artemis III mission, and Artemis III is part of NASA's big Artemis program that will, it's been broken up into like 4 segments of the architecture, where first, the part we're in now, human return. There's foundational exploration where they'll start to build up infrastructure on the moon, including a lunar terrain vehicle and eventually a pressurized vehicle. And then leading toward a base camp, or this is a drawing of the gateway, and eventually humans to Mars. What I like about this diagram depiction is that even though 3 of these are all kind of artists' renderings of future things that might happen, the first one is a picture, something that did actually happen. So that's from the Artemis I mission, which was an uncrewed test of basically mostly the Orion crew capsule and the SLS rocket. No keyboard is not. So Artemis II is actually coming up really soon now. Artemis II is going to happen as early as February of next year, as late as April is the current planning date. So there is a ton of activity going on now for Artemis II, including even on the science side that's going to feed forward to Artemis III. But Artemis II will be the crewed test mission where they will do free return around the moon and back. And then sometime after that, about a year and a half in theory, after Artemis II will be Artemis III, which really ups the complexity a lot. And this diagram here doesn't even show a huge component by it. But instead of the free return trajectory, the crew will launch on SLS and the Orion capsule. They'll get to the moon, they'll go into orbit, a big, long, extended orbit around the moon. They will meet up with the human landing system, which is the SpaceX Starship, transfer to Starship, go down to the moon, come back up, transfer back to Orion, and then head home with samples of this. Artemis III is going instead of to the equatorial regions that all the Apollo crews explore, going to the south pole of the moon, so a really different environment. What's gonna play forward here is the lighting circling through 1 lunar day, so 28 Earth days there, and then showing some of the candidate landing regions. So you can see just how dramatic lighting is there. The sun will always be kind of skimming the horizon there, and everything is going to be casting huge shadows. The actual candidate landing regions right now, actually go forward, sorry. They've updated them, so there were 13 candidate landing regions. There's now 9. these are them. The South Pole is right about here. Near side is that way. And so you can see they're all generally on high areas that get a lot of illumination. I don't know where they're gonna land yet. NASA does not know where they're gonna land yet. It will be somewhere in one of these areas. It's extremely complicated, partly for a lot of different reasons, but it's likely that for a long time, they'll be carrying forward multiple landing sites. So somewhere at least, 5 or so. And that's because of the extreme lighting. They want to plan to be able to launch at any time. And so they're still in the process of selecting where amongst these areas it will be. So after all that, they will get to the surface, they will land. 2 crew members will stay on the moon for about 6.5 days. And I guess the next question is, what are they gonna do there? And that's where our team comes in. They're gonna do science. So I'm the PI of the Artemis III Geology team. We have a really incredible group of people across the country, across the world, in the UK and Canada. And actually in probably, 6 months or so, we're going to be adding in another group of team members, participating scientists that will be selected. Hopefully soon. I think the proposals are in or partly in, so to anyway soon. So I don't know if anyone here applied, but excited to welcome new team members. The one thing that I want to update from this slide, our deputy PI, Lauren Edgar, she's at the USGS, and this morning, like an hour and a half ago, they announced the next astronaut class, and Lauren was selected to be an astronaut. So, Lauren, she's done a lot of work on Mars science as well, so that's pretty crazy news to me. I can cry this morning watching her on stage there. So this is also really sad in one way, that she's not going to be an active member of our team anymore because, she's going to be learning to fly a jet and stuff. So anyway, we'll have to update our slides, but really excited to watch what Lauren does and how she contributes to Artemis as another part of NASA. But a little bit about our team. Our team's we're competitively selected as a team to join the Artemis III science team. And the whole Artemis III science team includes an internal NASA science team. And includes now deployed instruments, there's, seismometer, there could be growing some plants on the moon, and the future participating scientists that I mentioned. And so our role, and go through a little bit of, some of the work that we've been doing background. Our role is to participate in defining, the science objectives for the mission, designing the surface campaign to satisfy those objectives, and what are they going to do during their EVA time. What samples they'll collect, support real-time mission operations, and then perform the support. The Artemis duration lead is Juliana Gross. She'll be leading the preliminary examination of return of samples and will support that work. And then at the end, we'll write it all up and into the initial science results from the mission. And that really will just be the beginning because that is going to be the kind of preliminary science, but then the samples, all the data, everything will go out to the community and people will do the real hard work that is going to take years of investigations to answer a lot of these questions. So a little bit of background on the science goals and objectives that we defined. We took our goals largely from the last Planetary Science and Astrobiology decadal survey. So every 10 years, coming together through the national academies, deciding what are the big goals for NASA to work on in this decade. They outlined 3 kind of overarching themes. Looks like I've animated this: solar system history, geologic processes, and volatiles. And so we've kind of fit our goals that we want to focus the mission on into those themes. And I will kind of go through quickly each of these goals, in the next couple of slides, but basically the first two are enabled by being in a different area of the moon that has, different rocks that haven't been studied before. And then the bottom two are really enabled by the environment at the South Pole. Okay, so our first broad science goals look at the early evolution of the moon. And all the past places where there's been field exploration campaigns were really dominated by this kind of creep terrain on the moon. The moon is unusual on its near side and that had a lot of volcanism, also has an unusual composition represented here by thorium abundance. And so that's looking at, kind of the evolution of the moon a little bit later than we want to look at. We want to look at the very earliest crust that formed. And so when we look at where the landing sites for Artemis III are, kind of like just tip the moon up here, you can see the Artemis III candidate landing regions. These are all within the feldspathic highlands terrain. So that very ancient earliest crust that formed on the moon. And that can teach us really about how the crusts form early on terrestrial planets. It's the most accessible place to do that because the Earth's earliest crust is really lost to time. Looking at the impact history, another interesting kind of conundrum that's come up in lunar science is just what impact events did the Apollo sample state? There looks like there's a big spike in impacts around a certain time, but now there's a general idea that maybe actually the Apollo rocks are really strongly affected by one big impact event, the formation of the Imbrium Basin. So the Artemis regions are getting just about as far away as you can from that and are right on the rim of the South Polacan Basin and sampling different populations and basins. So collecting material that was formed in this kind of other population is going to give us some insight into that early history. Another thing that is really kind of lost on Earth. Regolith processes. This is one of my favorite areas to study, but looking at how the moon's rocky crust is broken down over time into the regolith, the dust, and then how it is affected by the space environment. So uppermost surfaces of all the grains are altered as they sit on the moon's surface, and that affects what we can observe remotely of the moon. The moon is, and now actually many asteroids have also, the moon has been kind of a laboratory where we've really developed our first understanding of the space weathering process. The poles have a different weathering environment potentially, where they see a lower solar wind flux, and there's some remote sensing hints too that just that regolith, there might be slightly different regolith properties at the South Pole. So that is one thing that we'll be looking at. And then finally, volatiles. Mentioned the weird lighting environment at the moon's South Pole. They're shown in the background here. This is a percent illumination map. So areas that are black get no sunlight ever. Areas that are the brightest pixels in here get up to like 60, 70, 80% illumination at times. But those dark areas are incredibly cold. Big swaths of areas get down to temperatures like 65 Kelvin. I think that the coldest temperatures on the moon are supposed to be about 18 Kelvin. We'll not be sending astronauts into those areas. But there are plenty of smaller areas that can act as cold traps for volatiles. So any kind of water delivered by comets, by volcanic outgassing, from solar wind interactions. Those are something that we hope to sample in some of these cold traps. And there is good, very low resolution data that shows that there is hydrogen, water equivalent hydrogen abundances. And some of these areas are in the very big cold areas, but there are kind of smeared out, from this low resolution view into some of the areas that the astronauts will visit. So this is a big thing that we can test. How much water is there? So there's a lot to do. There's a lot we want to do. You know, the lunar science community has had many pent up questions that some of which can be answered from Changa 5 and Changa 6 samples, but not all of them. And so there's a ton we want to do. The time will be limited. It'll be about 6.5 days on the surface. There will be 4 EVAs where they will go out and explore on foot. So the distance is limited because they'll be on foot. They will not have mobility beyond that for this mission. So they are limited to the distance that they can safely walk back from. So about, less than about 2 kilometers. And then other mission priorities. I don't know what other people want to do besides picking up samples, collecting those rocks, but of course there are other priorities that are going to affect the time that's available for the geology investigation. The mass is also limited. Can't bring back endless samples. There's just under 100 kilograms allotted to sample return. That also includes things like pretty massive sample return containers. Interestingly, I think the time is going to be a lot more limiting than the mass in the end. So the job of our team is to really make sure that we're maximizing the science that can be accomplished during this mission. We feel like a really important responsibility here to the community to make sure that we are bringing back the samples, the data that can really lead to substantial progress on these science questions. So we've developed a flexible and prioritized science traceability matrix that links each of our objectives to the implementation strategy. So under those goals, we have 12 science objectives. I will spare you the details of all of them, but I did want to highlight 2 of them and just show you how we can plan on tracing out from the objective and what we want to accomplish out through the kinds of samples and analyses that will need to be done on those. So the first example is the age of the South Pole Aitken Basin. As I mentioned, this is the huge South Pole Aitken Basin. The biggest basin on the moon, potentially in the solar system that's recognized. And understanding when that basin formed is basically going to give us a start of when did the moon start recording history. After that initial crust formed and solidified enough that it could support impact events and recording those as craters and basins. This is our first look at when that impact record starts on the moon and then across the solar system as well. There's a lot of questions about the earliest part of lunar history, whether there was a big spike in impact events around 3.94 billion years ago. If SPA formed earlier, did it really alter the course of lunar evolution? I think it's pretty clear that it did. There's some ideas that it caused a lot of the magmatic episodes around that time as well. On the Earth, we have a really limited impact history record, of course, because the Earth's geology is so active. This is showing all of the areas where we have either an impact crater or deposits, remnants from impacts. It's really limited because of all of the Earth's active geology. And when we look at the moon and add in all of the impact events that it records, or that are still preserved today, in orange is every crater greater than 5 kilometers in diameter. And this is the South Pole Aitken Basin on the far side. That is the thing that lets us get back very early in time and understand not only the moon's impact record, but also the Earth's. They were together, they're together in space. It's the same impactor population that was hitting the moon that was also affecting the Earth. And so when we can look at that earliest time, it's really critical for well, a lot of interesting things like solar system dynamics questions. But also, when did that start really heavy bombardment, these huge basins start to die off? These kinds of impact events had a huge effect on habitability of the early Earth, right about the time that we think life was forming about 3.9 or so billion years ago. An impact event of that scale would have vaporized the oceans and made it a very unhappy place to be, basically. So understanding how that can in the early interplay worked is important for planetary science. So to determine the age of SPA, we want to collect samples that were melted by the impact event, putting that radiometric age, resetting the clock there. And this is the kind of planetary wide scale of the SPA event, where all of this material was ejected just across a huge swath of the moon. And when we look at where the Artemis candidate landing regions are, what is left of SPA today is a kind of ring of massifs here that extends. And a lot of these are right on top of some of that original rim of the SPA basin. So that's what will allow us to sample that material, even though there's been so much subsequent evolution, we have billions of years of subsequent impact events. That material, enough of it should be preserved in the regolith in these areas. And so how do we get at that material? We need samples that were melted during that impact event. They're highly likely to be present at any of the candidate landing sites. And so this becomes a statistical problem. This isn't something where we can expect to find in situ material that we can find in an outcrop that is clearly melted and placed by that basin because of how old it is. So we'll need to collect a statistically significant number of rocks that are large enough for radiometric age determination. And so the best way to do this is a rake sample. This is Jack Schmidt collecting samples with the Apollo 17 rake. This is kind of the updated design, the government reference design for the Artemis rake. And the tines are separated by 1 centimeter. So you should get a huge abundance of samples that are about 5 grams and larger, enough sample that you can do some of that really important science on it. And I'll just mention that the rake is kind of favorite tool because the impact mixing process has been so thorough. So we're just using that process to our advantage to kind of sieve out the pieces, and those will be supplemented with larger samples of impact melt bearing impact sites at branches, 5 to 10 centimeter scale, rocks, hand sample size that can fit in a sample bag. And this is one of the best things about these bigger samples is that they give you an opportunity to determine the ages using multiple chronometers on the same sample. And so they also can give you a better interpretation of the ages and the provenance because you have these samples that are recording multiple impact events, and you can kind of reconstruct that history from the rocks. So when we put that together to try to figure out how to understand the age, first, how do we know? How do we link a sample to that impact event? The SPA basin excavated so deep into the moon that it has a pretty distinct compositional signature. So we'll look for samples that are compositionally matching the remote sensing observations. So it's a little bit higher iron and higher thorium and some other incompatible trace elements. And then look for among that population the oldest ages that are found with statistically significant frequency. You can see the Apollo samples I mentioned they kind of peak around 3.9 billion years. And this question is, will we see a similar distribution of ages in this other area of the moon? Or will that be shifted to older ages dominated by the South Hopkins Basin? And the other really helpful thing here is that this isn't something that I can necessarily answer with 100% certainty from the sampling one area. The Changma 6 samples, they have a proposed age of SPA from some of the very small fragments that were guarded into the regolith there. And there's a long duration rover concept called Endurance. There's a science definition team working now to understand that. And that one of the main goals from that is to kind of collect additional samples from across the South Hopkins Basin. So this will be a multi-dimensional problem to put back together. The other objective I wanted to talk about too briefly and how we hope to answer this is looking at cold trap volatiles. So our objective there is to evaluate the nature, origin, and abundance of persistent volatiles in cold traps. Once you get cold enough, so we're aiming for areas that have a maximum surface temperature below about 100 K, but not so cold that they are dangerous, not just because they're extremely cold, but because they start to pick up some kind of dangerous, potentially dangerous volatiles that would be toxic. So aiming to get to areas here where it's so cold that any kind of molecule that has been trapped in there is likely to persist on very long, multi-billion year time scales. The existing data from this problem is basically all remote sensing data, and it's a really complicated picture that shows heterogeneous distribution of water ice on multiple scales, and a picture that's much more complex than can be pieced up together from remote sensing data alone. So what we want to do is assess volatiles in areas of varying thermal environments, get to at least 2 cold traps that are different temperatures and different ages that can help us understand, the nature of those volatiles, including their origin and the properties controlling their distribution, including present day processes such as impacts and things that would work to mix volatiles. So our strategy for doing this, we will be collecting vacuum sealed samples from these various thermal conditions and ages. These will be the first return samples of cold traps. So our plan is to go to 3 places. Go to the coldest and oldest accessible location at a landing site. There's a lot of different thermal modeling that can show whether water ice is predicted to be stable in the upper 70 centimeters of the surface. 70 centimeters being the depth to which we can sample easily. Go to a comparison cold trap with a different thermal environment and a younger host crater. And then go to warm illuminated terrain where ice is not predicted to be stable at all in the upper meter of the surface. And that is basically our control sample to show, these the sealed samples have to be proven out that they're not going to leak and things. So we have to have our control sample to show how well that sealing is. The other complication is that there is no freezer on Artemis III. So all of the samples, once they're collected, will warm to ambient temperatures. So to deal with that and to preserve some stratigraphy and separate volatiles from depth, those that are ones that for this objective, at least we're most interested in from the superficial volatiles, which in this case could potentially be deposited by the lander itself. The LOX methane reaction leads to water. So there's going to be water deposited from the lander itself, and then the suits will outgas as well. So we want to make sure that we're carefully separating that upper surface from the interior. So we'll get those three stratigraphies, the very surface, the upper 35 centimeter or so, and then the 35 to 70 centimeter depth. The drive tubes, are remarkably similar to what they look like in Apollo. This is, current testing, that was done in Iceland. And so what you're seeing is the top half of the double drive tube, the bottom half, and then this is just an extension handle, that is hammered into the ground. I guess on that one on the far side, all you're seeing there is the extension handle sticking out. When we look to analyze these, and this is another thing that will likely be led, not necessarily by our team, but by the science community, is to compare the volatile composition and abundance as a function of depth. The abundance between those different, and composition between those different sampling sites. And we'll really be looking at some of the, it's a complicated picture to unravel, but you can attribute some of the different isotopic ratios and compositions, especially to different sources, such as solar wind and micrometeorites, or upside delivery from comets, asteroids, or earlier outgassing, which would have had potentially much sulfur, etc. When you add up, I've given you a quick look at 2 of the objectives of the 12. When you add that up across all of the objectives that we want to do, this is our current estimate for what the geology investigation will require. Requires going to about 10 different science stations. So some of those are areas, different coal traps, but also impact craters that have excavated materials from different depths to really get a look at the diversity of the site. About 35 to 40 unique samples, about 6 hours of task time at stations, exclusive of traverse time. This one is tough, that's a lot of time that we're asking for. But I think this is what we really need to kind of provide the community with samples, and the data from these in situ investigations that is really needed to answer the questions. Ultimately, how far we get down this list, how much will be accomplished will depend on the EVA constraints, time allocated, geology, accessibility at the targets of interest at the final landing site. We've done an assessment of all of the current candidate landing sites within those regions. And there's a big difference in terms of how accessible things are. Some of the, permanently shadowed regions, these cold trap areas, some of the landing sites, great, huge areas, they're cold. So the slopes aren't too steep, they're accessible. Others may have no areas like that. And so we're really we've put in recommendations to make sure that we can get to one of the sites that will be better for science, if at all possible. Yes.
How do you figure out how long it's gonna take astronauts to walk a kilometer across this part of the moon we've never been to and then do a set of experiments in a place that we've never been? How do you estimate that?
Well, there's a lot of uncertainty in it, first of all, but there's a lot of different ways that happens. One is Apollo, just using that as an analog, especially for traverse times, that's kind of the best bet. One of the main source for that one actually comes from Apollo 14. They had a very long traverse up to Cone Crater, and they were pushing this tool cart that was very unwieldy. The Artemis astronauts will also have the tool cart. So that one, it was a slow time, and you can look at traverse rates with slope both up and down. They also, in terms of how long other tasks take, do a ton of testing in different kinds of environments, including in the neutral buoyancy lab at JSC, where they've taken an aquarium stand and put it in one end of the pool, with a kind of a grain size distribution actually. And then they had, I think, I heard that the rocks that they put down there were designed by one of the people who makes, who designs like zoo, like hippo. Enclosures. They have these like really cool rocks down at the bottom, and they actually can test out like doing some of that. There's also field tests, there's Argos, which is, they've got some of their gravity offloaded and they can test out. I think it's like a perfect analog. So it's kind of putting them all together.
Yeah.
And then, hopefully you can kind of make your best estimated guess. But a lot of this too is like, this is our going in plan, but the hope is that they'll find something really cool and be like, all right, stop everything, we need to do this. And we're preparing to adapt to that too. And that's actually, I think, what I wanted to talk about next. How do you take this kind of overall plan and turn that into a site-specific EVA plan where you're outlining everything you want to do? This is sort of a little a schematic of that where we start with our site agnostic science traceability matrix. One of the things I love is that the science traceability matrix is now included in the flight control team software. So it's really great to hear the whole flight control team talking about all the science goals, and they really get, behind that. And they've all actually done a lot of training themselves going through Geo 101 and their fundamentals classes, which is really cool. So we start with that. Kind of do our geologic mapping of the site, informed by the regional context, and just throwing all the data analysis out at the site that we can. We then pick kind of our anchor points of interest. Some of the areas we want to visit, there's a lot of flexibility in. Some of them are like, we need to get to the rim of that crater. If that crater has big boulders, then we want to resample those. Or we need to get to a permanently shadowed region. So we kind of put those points of interest. We send those to the flight control team. They tell us like, no, that one's too steep, that one's too far, or whatever. But we kind of iterate until we found our anchor points for the traverses. Then we can start adding in kind of secondary points that can cluster around those anchor points, things that are less geographically constrained. We work with the science and task officers, and they develop the final EVA plans. And then those go and they get turned into operations products. There's the map book. They'll still be using, a lot of people are thinking like these Artemis astronauts will have heads up displays and it'll be really advanced, but it's not like that. They will have, similar to a little cuff checklist, little booklet with our flipping thread. And we've been testing this process now. Using so far, a lot of it's been done in virtual reality. We had our first like full scale sim last November. Brought together science team, flight directors and controllers, and we carried out only the science, focused on the science component of the EVAs. One of the amazing things about doing this in VR is that you can then fully test out the planning process using all of the lunar data. We're also doing field tests where you're kind of making up science objectives that could be relevant to a field site, but here we can test the process of planning with the real lunar data, and including getting, the whole flight control team up on what are the constraints of the data, what is the quality that they need to understand the slopes and assess safety things as well. So we, I think I actually you just said that. Oh, we planned out a lot of this at the first time at this candidate landing site on the Nobile Run 1 area. We used our STM, we defined all the points, we worked with the whole flight control team, developed activities at 9 science stations. And now the findings and recommendations that we had out of that are all being incorporated into our current planning process, which we're now running again for multiple sites at the same time to kind of simulate that issue of having to plan to multiple different landing sites for our next VR sim that will happen next month. But the things we've learned have been amazing, just especially kind of working on communication across the team, the timeline of all the milestones that need to happen. The planning software is still being developed, working with that team is amazing. The sampling plan, made changes along the way there, the mapping, the lessons learned, the training that needs to happen, a lot goes into that. When we tested the real-time operations, there was a huge team supporting this. There's virtual reality engineers that take all of the real lunar data and get it into the VR environment for the surrogate crew. They do add in like additional sub-pixel things like rocks, craters, etc. My favorite was that they took some of the Apollo sample scans and then they, including like they already have a sawed off face. And they like stuck them on wood. Some cases they blew them up bigger too. So it's like, oh, the crew would pick up this rock and be like, oh, I'm looking at like fist-sized crystal Denevi. They also, there's an anomaly team that simulates problems, things that could go wrong. They're known as the bad guys. They have things that, you know, they throw at the crew to complicate what they're doing, as well as the science team, like, we can't get to this area, or, you know, this tool is broken, what do you want to do about it? And then a lot of the practice too was just trying to work out how we fit within, the flight control structure, which included, just for this last room, kind of a smaller one, but where there was the front control room with the flight director, ground AV and EVA lead. Basically the EVA planning room in the middle, and then our science evaluation room, where, the first time through this was overwhelming, but we're getting better and better as we go through and practice this. That was all done in kind of makeshift conference rooms, but we did get to visit the new science evaluation room and mission control. It's going to be amazing. Artemis II has already used this. We'll get to use this room for the first time next month. But this is one of the best parts. Well, the video wall is one of the best parts for us, but there's a giant mapping table too, where we can put all the data in there and gather them. So very fun. We're also doing a bunch of field tests and exercises. The Jet 5 test was actually done in 2024, is that right now? That was a test in Arizona. Look, you can see there's the map book. So exciting. They're trying to figure out where they're going to collect the samples. So that kind of tests a different level of fidelity, because at different aspects of the tests. Some of it was done at night, some just with big kind of floodlights to simulate the mirrored lighting at the moon south pole. Some of it was done in daylight, some of it was done in, you know, shirt sleeves and backpacks, some of it was done in these kind of replica suits that at least they help kind of recreate the constrained mobility that they have. And then we've also been doing a number of exercises, and for our team as well, going to, you know, doing remote sensing analysis, sending out a couple of grad students to explore an area, seeing it through their eyes, and then going out there ourselves and testing the tools, et cetera, and kind of understanding the difference in what you learn from remote sensing to through the eyes of and descriptions of a crew member to be yourself. I think that will really help us plan better too. And then why I'm here this week, we will be supporting the preliminary evaluation of samples. So after the mission's done, we will work with our administration lead to create a sample catalog that needs to be published in less than 6 months after the mission. And it must include enough initial data about the samples so that the investigators that are going to be doing in-depth science can select the best sample. They can propose the science to the best sample for their science investigations. This is going to be a huge amount of work, but it'll really come to. And then after that, we'll work on the preliminary geology science report that's due within a year of the mission. So overall, we're making really great progress towards the Artemis III mission. Everything that we are doing, we always try to keep in mind the motivating goal of our team, which is to maximize the science of the mission and collect this data that will serve the community for decades to come, just as the Apollo samples and data have. We continue to value community input on these plans. We're really looking forward to having new team members join as well. So I think that may be it. All right, thank you.
Okay, we have lots of time for questions. Anyone has any questions?
Might be someone on.
Oh, and online, but I can't.
Can I see? Oh, yeah. No, that's good.
That's good. I think if anybody has any questions, we'll put it in there, but while we're waiting.
How do you thought about balance, like, it seems like the huge motivation is sampling, right? How has the team thought about balancing that with just any other type of geologic observations, like is sampling just number 1 through 10, and then the context and sort of.
Yeah, I didn't talk about that. That's a really good question. So, anytime they get, well, first of all, the training that they go through is pretty amazing, of just getting them to be comfortable with the geologic description. So we're trying to kind of squeeze in the geology and the, just keeping their eyes open and giving the descriptions anywhere possible. So, you know, they're setting up a deployed instrument or they're like hammering in the flag, they can tell us about the geotechnical
Right.
properties of the soil as it goes in. But as they're getting to a station, there's a kind of initial time that's just saved for station characterization. So walk around the area, collect panoramic images, kind of get your bearings, you know, scuff your food. Tell us about any differences that you see here from other areas. So that context is like really critical. I mean, that's what makes these samples a lot more valuable than otherwise they would be.
And that's included in your like 60 hours, which is,
6 hours.
but it's 10 times 6, right?
No.
Oh, that's
It's
what I read. Oh, too.
It's 10 stations that
So they
fit
each
within
get-
6 hours plus traverse time to those stations. Time is, they're gonna be like half an hour,
So each station gets 30 minutes.
something like that, yeah. Well, we'll have fewer stations.
The latter seems
It's
a real
a,
possibility, yeah.
yeah, it
It's like-
depends on how far. As well.
Yeah. In my mind, the context you just described is like 25 minutes, right?
But I think we're keeping with like the initial, I mean, well, so first they're walking to there, which they can be giving.
Sure, yeah,
the
yeah, yeah, yeah.
context all along the way. Keeping, depending on the kind of site, like 10 to 10-ish minutes of just giving that context.
And
that
then 20
initial
minutes or
description. Well, it depends on where they are.
Sure.
What actions need to happen at that station, yeah.
Okay, so it's.
Yeah, and then they'll fall behind and then they'll start, you know, all right, now you only have 5 minutes left at this station. Oh, just add to, the other things that I didn't really get into, but, you know, some of the, especially the regolith, objective really wants to look at things like trenching. So how does, you know, what's the soil look like there? Can you see any stratigraphy in there? Imaging, including imaging of footprints. The lander coming down is also a great experiment of the plume interacting with the surface and scouring. So how does that change as you go away, and can they image that and describe it as they get further away with like high resolution stereo images?
Very cool.
I know you said that you'll be competing with other priorities, but when they do go out in the truck, will it just be for one sole purpose, like sampling, or will they have multiple tasks?
So each EVA will probably have at least a couple, priorities during that EVA. You know, some of them are like engineering related, inspecting land and dirt. Some of them are, public affairs related, talking to the president. Some of them are, deploying instruments and other equipment. So I think how it splits up among the four EVAs is a big kind of optimization problem that is landing site specific in a lot of cases. Yeah.
Okay, we have a question from online. Says, can you comment on the progress that's been made on dealing with the dust and fine regolith? For example, the abrasiveness, which caused all kinds of problems on follow.
Yeah, I do. There's been progress certainly in a lot of tests, but I think a lot of it is just, preparing for time to deal with it. There will be time for, cleaning, basically, including once they're already returned into, the crew cabin of HLS. But there's a garage, area, like the airlock kind of area where they can leave a lot of the dusty equipment and things. And so that's one of the aspects. There've been, since then, a number of, tests of different kinds of new technology to help with that. But as far as I know, I don't think any of the kind of like active technologies, like electrostatic, things are not being used here. Like, we're testing the lander, we're testing the new suits, and everything else.
To follow up on Tim's question about context, will the astronauts be equipped with like body cam and so forth, so that a lot of that is done automatic?
Yes, they will each have, like the helmet camera, that will be, I think at least 1080p or something. And then we started TBD on whether there will be an additional context camera. And then they will also have, Nikon Z9 cameras, each of them, for collecting still images or potentially video too.
For the participating science, is that for each Artemis will have a PS call, or is there multiple PS even within each Artemis?
There will be one participating scientist call per Artemis mission. Yeah, I can't remember the schedule. I know that this one, at least the first half of the proposal stuff hasn't come in for that.
Kind of a two-parter. Is there any sort of consideration being given to magnetically anomalous areas near the South Pole? And then like also, is there any plan for instruments that continuously monitor like solar wind at the in those regions?
Yeah, so that's a great question. The first part of it is, there are some kind of different magnetic anomalies in the South Polar region, and they're, big and broad and at the scale mapped. That, it's like, well, are you ready to guess this candidate landing area might have a, stronger magnetic signature than this one. But that's not one of the highest priority, even amongst the science, factors in assessing the sites right now, for this mission anyway. And yes, we would love to have, continuous solar wind monitoring, but the deployed instruments were also competitively selected. And they don't include that, for this mission. There is, seismometer suite, there is, dielectric, analysis. There's a, kind of just stationary retroreflector that will be left behind. And then there's a plant growth experiment, that part of what will be left behind and part of it.
Okay, this leads into the next question. Any instrumentation plan to be left on the surface? And there's some that wants to pause.
Yeah, so the ones that will, I wish I could speak more intelligently about the plant growth experiment, because it is really kind of cool. But that'll be left behind, and, they'll have a control plant growth experiment on the Earth to see if there's any differences. The retroreflectors will remain and can remain, indefinitely, because they require no power or anything. The The seismometers were moving and they will hopefully last for months, 2 years. I forget the kind of the baseline, plan there, but the hope is that they'll last for years. Can continue kind of sending back data, long after the mission.
Any questions? Okay, let's thank our speaker.